In this lecture, presented by www.free-academy.com, we're going to introduce the concept of implicit differentiation. Now, something I've been harping about since the beginning of learning derivatives is that there's more than one way to go about solving the exact same problem. We found this using the product rule and quotient rule, where we would take, say, if we had like sine of x divided by x, instead of using the quotient rule, we would rewrite this as x and negative 1 times sine of x. So what we're going to learn with implicit differentiation is simply another technique of finding derivatives. So the best example that I was able to come up with to explain this is to use the equation x times y equals 1. And we want to find the derivative of this. Well, you only know how to do derivatives the one way so far, in which is known as explicit differentiation. And the way you would do this is you would solve for y and get that y equals 1 over x to find the derivative of y is equal to negative 1 over x squared. This is explicit. But we're going to learn another way, which is implicit. Where does the difference arise? Well, in this case, we're saying that y is a function of x. Y equals f of x, which equals 1 over x. We're explicitly, overtly, and outrightly defining y as being equal to 1 over x. And this implicit equation here, we're still saying y is an equation of x, but we have the x's and we have the y's muddled together. And when we're going to solve a derivative using this way, we use implicit differentiation. So the best way to explain this is to multiply both sides by the derivative with respect to x. And just like when we were using the product rule before with our f's and g's, we're going to treat these kind of two different functions, only y is a function of x and x is the variable. So this will give us d by dx of x times y plus x times d by dx of y equals the derivative with respect to x of 1, which is a constant, which is equal to 0. So the derivative with respect to x is equal to 1 times y plus x dy by dx, which is the same notation that we've been using in the past for y prime. And this all equals 0. So this was just simplification from this step to this step. From say step 1, we took the derivative, and from step 2, we just simplified the equation. Now in step 3, we're going to take y plus x y prime, and we're going to solve it. So let's go on about doing that. First of all, let's separate out our terms here, and we're going to get y prime is equal to negative y over x. Well, that still doesn't tell us much in terms of y in terms of x. However, if we go back to the original equation, we have that y equals 1 over x. So y prime equals negative 1 over x times 1 over x, which is equal to negative 1 over x squared. So we got the exact same route using implicit differentiation as when we used explicit differentiation. And at this point, you're probably thinking to myself, if I had to solve for y in terms of x, what's the benefit of this? Well, it's probably not very clear in this what the benefit is, but eventually we're going to start taking these derivatives with respect to time, which I'm going to cover in the next lecture. And then we're going to start solving some real practical problems with it. But before we go on and let's do that, let's take another example that might explain a little bit more clearly what the benefit of this is. Say we have the equation x to the third plus y to the third equals 3xy. This is an equation where if you want to solve for y, it's going to be incredibly difficult because you can say y to the third equals 3xy minus x to the third, but then trying to get this y back out again is, very difficult, if not completely impossible. I don't know if there's any way to separate this down further. Maybe if you used a computer you could, but I'm not familiar with it. However, we can solve this problem using implicit differentiation. So we multiply both sides by the derivative with respect to x, or better yet, we take the derivative with respect to x of both sides. So this gives us d by dx of x to the third plus d by dx of y to the third equals, and because we did this in the last problem, it should be pretty straightforward, 3y plus 3xy prime. I just did that in the previous example, so nothing special there. Just skipped a couple steps. Now we go on to see that this first term here, the derivative with respect to x of x to the third, is simply equal to 3x squared. But what the part that is most confusing to students learning this is, what do you do with the derivative with respect to x of y to the third? And the best way to remember this is the chain rule. So you have f of x to the, well, let me rewrite this in a slightly different spot. Let's say that f of x is equal to y, and g of x equals x to the third. G of x, or g of f of x, is equal to y to the third. So if you're to take the derivative of g of f of x, it's equal to g prime f of x times f prime of x. Well, your g prime, g being x to the third, g prime is equal to 3x squared, and your f prime is equal to the derivative of y with respect to x. So if you plug everything back into your chain rule equation, what you're going to get is 3y squared y prime. And this, of course, is all equal to 3y plus 3x y prime. Now, I'm sure that this part wasn't very friendly to most of you. I'm going to do lots of practice problems explaining exactly how to get the derivative of that term, so be sure you check in for practice on that. But before we do that, let's take this problem to completion and let's solve for y prime. So we'll get 3y squared y prime minus 3xy prime equals 3y minus 3x squared. You can factor a y prime out of both sides, or out of both terms on the left-hand side. And what you'll get is that y prime is equal to 3y minus 3x squared, all divided by 3y squared minus 3x. And there you have your derivative of y with respect to x. And that's the value of implicit differentiation.